Greetings, minions. It is I, the evil genius. And let me tell you, no self-respecting plan for world domination will ever succeed unless you have first mastered lightning. So today, I will be Zeus, Lord of the Thunderbolt. But first, let me show you this balloon. This balloon has lots of atoms in it, right? Many, many billions, all with positive charges and negative charges. Now, the positive charges are pretty much held in place. They don't move around a whole lot, they just vibrate. The negative charges can move. We can rub them off, we can put others on, giving the whole balloon an overall electric charge. And I'll do that just by rubbing it in my hair. Now, this balloon should have an electric charge. Anything with the same charge should try to repel. Anything with a different charge should attract. See? It sticks to the wall. This is what we call static electricity. The balloon has a different charge from the wall, so they attract. Now, if I take away the charge on the balloon, just touch it all over, because I'm earthed, I'm either taking away electrons, those are the negative charges, or adding electrons. The balloon falls off. Now, let's look at this and scale it up a little bit. For those of you who see a family resemblance between myself and this Van de Graaff generator, think it may be funny now, but when I rule the world, who's going to be laughing last? Anyway, this is a Van de Graaff generator. It works exactly like the balloon. What happens is this belt here picks up a charge down the back. It's an insulator, so the charge sticks on it, travels up, and then if you look inside, the charge jumps from the belt onto this conductor and ends up on the outside of this metal dome. So the charge builds up. And it's the same charge. Therefore, it gets stronger and stronger, and it wants to get to anything else. So I'm just going to turn it on, and we'll see what happens. As you can see, the charge is jumping from the Van de Graaff to my hand, or from my hand to the Van de Graaff. It doesn't really matter. Now, normally, air is an insulator. But as you can see, if there's enough of an electric field, you can make the air a conductor. Reason why? There are a couple of ions in the air all the time, positive or negative. If you accelerate them enough, they move far enough before they crash into another air molecule that they knock an electron off of it, making a couple more ions. It's called an avalanche effect. What you're seeing here is lightning, just really, really small. And the sound you hear, that's thunder in miniature. Now, it takes 30,000 volts per centimeter to make the air a conductor. So I'm getting sparks here that are at least 4 centimeters long, which means we're generating over 100,000 volts between the dome and my hand. Now that sounds like a lot, but there are so few electrons that are jumping from one to another. It's like being hit by a sand grain going at 100 miles an hour. One sand grain, no big deal. However, you get a whole bunch of sand grains, then you have a large rock, and then you have a problem. So here we have a high voltage and a low current. Now one other thing we can do here, this is a fluorescent light tube. It only works with a pretty high voltage. And let's just hold this up here and bring it down. You can see there's enough current to light this up between there. Notice the current's going from the bottom, from the dome, to my fingers, and then down my body and out. If I hold it halfway, you can see it's going through my hand because only the bottom lights up. Now, just to prove that like charges repel, we have here some tin foil, and I'm going to turn on the Van de Graaff, and we're going to see how it affects these bits of tin foil. Here we go. Look what I've made, a mess. Now, one more thing, just to show that same idea. Where you get a sharp point, you get a very, very strong electric field. And what that's going to do is it's going to make the ions in the air move. And that means this should move the other way. Newton's third law, for every action, there's an equal and opposite reaction. Let's just watch this go. So we've got some movement, but these are still static charges until they jump, until you get the lightning bolt. And like I said, yes, it's a lightning bolt. Yes, it's coming from my fingers, but we've got the lightning bolts, we've got the voltage. What we need now is the current, and that's what we're going to do next. What we have here is an EHT supply, extra high tension. It goes up to 5,000 volts. Now compared to the 100,000 volts we were getting from the Van de Graaff, that doesn't sound too impressive, but we get a bigger current. Thing is, we still get it a trickle at a time. So what I'm going to do is I'm going to take that current and put it in this capacitor. So I'm going to charge up the capacitor to about 2,000 volts, because it says on the side, 2,000 volts maximum, and I don't want it to explode, right? Not yet, anyway. So I'm going to charge this up to 2,000 volts, and then we're going to discharge it all at once, and we'll see what happens. Okay, here goes. Now if I put this in here, it goes across a 50 mega ohm resistor, right? It's good for safety. So I always put it in here. And here we go. So you can see from the dial, capacitor is charging up bit by bit. 200 volts, 400 volts, and 2,000. Always a little careful with this one. It looks perfectly harmless, but looks can be deceiving. Now what I'm going to do is I'm going to hold on to the insulating wooden end of this file, and I'm going to give it a conducting path so that the whole thing can discharge all at once. Watch. Okay. Now that worked really well. What we're going to try now see, look, I can touch both ends. I'm fine. It's completely discharged. What I want to do now is discharge it across one of these. Here we go. Watch closely. Excellent. Now, I know what you're thinking. You're thinking, we need more current. Well, I have more current for you. This is our low voltage power supply. I know you don't like the idea of low voltage, but 8.5 amps. So what I'm going to do is crank it up and put it through this little pencil, and we'll see what effect it has. All right, now notice the wood doesn't conduct electricity. It's a good insulator. However, the graphite does. Now let's see. Here goes. Excellent. Right, so the graphite is still conducting an electric current. Right? It's got a pretty low resistance, so the current gets quite high, gets quite hot. Now I know what you're thinking. You're thinking, how can we get more current? Well, I'll tell you. This pencil, I'm going to wire up to the mains. Now, there's the pencil. Here is the big red evil genius do not press button. What I'm going to do is I'm going to press the do not press button. We're going to see what happens. Mains electricity through a small piece of graphite. Here goes. Safety first. 3, 2, 1. Now, we've tried it with the pencil, and I know what you're thinking. What would it be like with a human subject? Well, fortunately, I have one. You have been judged by me, the evil genius, to be no longer worthy of life, and you will now pay the ultimate sanction. That's right. Your time on this earth is almost up. Why am I using a pickled gherkin as a human analog? Well, it has cells and it has salty fluids, and therefore it's going to be affected by the electric current in very much the same way that a person would be, but with slightly less screaming. Here we go. Any last requests? So, when you're cornered by the good guy and you have nowhere else to go, hit him with a lightning bolt. They hate that. Thanks for watching.